Well, we'll begin our study of Calculus 3 with a discussion about vectors, in particular vectors in the plane in two-dimensional space. So a lot of times, actually probably up until now, when we look at quantities in math expressed as numbers, they are now, from now on, just going to be called scalars, because things like force, velocity, acceleration can be expressed as numbers, but also have a direction. In other words, a force of 50 pounds moving in a direction is, direction of north is different from a force of 50 pounds moving in a direction south. So what's called a directed line segment represents these quantities, and the directed line segment PQ has an initial point P and a terminal point Q, like this picture shows. If we talk about the directed line segment PQ, then P is the initial point, Q is the terminal point, and the little arrowhead on there says in this direction. Right? Which, of course, this force would be different from a force going this way, right? Kind of the opposite. So, directed line segments with the same length and direction are called equivalent. If you could imagine, if you had some kind of a piece of stuff here, and you acted on that piece of stuff with a force of 50 pounds in this direction, it would be the same as if you pushed it with a force of 50 pounds in the same direction. So therefore, those vectors are equivalent. So the set of all directed line segments that are equivalent in the plane is called a vector. In other words, this isn't a vector, this isn't a vector, this isn't a vector, but all the line segments with this length and direction in the plane are what's actually the vector. Each of these is a representative of that vector, but any vector can represent the vector, and we use the one that's most convenient. So I'll try to use bold type when we get to it to represent vectors, but when I'm handwriting it, usually it's hard to do the bold typing like this. So we'll have a line with an arrow above it like this, right? So this would be the vector PQ, that's starting initial point P, ending point, terminal point Q, vector U, vector V, vector W. So we draw one directed line segment, which usually is a representative of the entire vector. In other words, this one represents the entire vector. Or maybe this one could be used to represent the entire vector, but the vector is actually all directed line segments of that length and direction in the plane. And that is handy for physical problems. So here's a question, an example. We'll do one example before we move on. Show that vector U equals vector V, where U is represented, that doesn't need to be bold-faced, U is represented by the directed line segment from 1, 5 to 3, negative 7. In other words, that's this is the initial point, this is the terminal point. And V is represented by the line segment from 4, 7 to 6, negative 5. And you're thinking, well, how on earth could we do that? And what we need to do is verify that their length and direction are the same. Well, that shouldn't be terribly hard, but we'll need a little space for that. The slope of the line segment, either one, let's go with this one first, would be 5 minus negative 7, so 5 minus negative 7 divided by 1 minus 3. Sorry about the truck going by. Okay, I think that gets it. Looks like 12 divided by negative 2. So the slope of this directed line segment, starting here and ending here, is negative 6. And let's try this one. The slope of this one, and if we get that, we'll be partway finished, but not completely finished. All that would be telling us was the direction's the same. Slope of this one would be negative 5 minus 7, so negative 5 minus 7 divided by 6 minus 4. Yeah, I know I'm doing it differently, but just to illustrate that it doesn't matter what order you put them in as long as you get them lined up properly. And that would be negative 12 over 2. And so that's also negative 6. So what we can discern from that is these have the same direction, but what we don't know is do they have the same length. And we can verify that with the distance formula. From 1, 5 to 3, negative 7 would be distance. We want the square root of, call it 1 minus 3 squared, 1 minus 3 squared, plus 5 minus negative 7 squared, 5 minus negative 7. Ooh, didn't mean to put percent there. 5 minus negative 7, now, there we go, squared. So, let's see, what is that? That would be 4, and that would be 144, so distance is square root of 148, and I know I could simplify that probably a little bit, but I don't see any real need to do that, because I'll just compare it to the other one and see if it's square root of 148. So the distance here would be square root of 6 minus 4 squared, so 6 minus 4 quantity squared, plus negative 5 minus 7, that quantity squared. And so I think you can see, yeah, guess what we get? Square root of 148, because this is 4 and that's 144. So either way, we got the distance and the direction is the same. So therefore, vector u equals vector v. Remember, this is only one of the representations of vector u. Actually, vector u and v gives us two representations of the infinite number of representations for that particular vector. And that vector has slope negative 6, so in other words it probably looks like down this way, something like that, and is square root of 148, so a little bit more than square root, or a little bit more than 12 units long.